All right, guys, and moving on into the second half of section 7.2, what we're going to start talking about now, hey, it's not every day you guys get to learn an entirely new number, but that's exactly what's popping up right here. One of kind of the cornerstones of Algebra 2 is the introduction of a new number called E. All right, so it's a little bit weird already that we're naming a number after a letter, but there's actually a precedent for that. So let's get into it. E right here, guys, is an irrational number. And the most common and most famous irrational number that you guys already know is pi. And remember that pi is actually the Greek letter P. So as I said, there's a little bit of a precedent for naming a number after a letter. So like pi, E is an irrational number, which means that it cannot be expressed as a fraction or as a terminating or a repeating decimal. And what we've got right here is really about as specific as we're ever going to need to get here, guys. E is approximately equal to 2.718. Now, like pi, this thing goes on forever. There is no limit to the number of decimal places that a computer has been used to calculate the value of E before. And it really comes down to, oh boy, there's a formula for this, that E actually comes from the formula of taking 1 over, and we start with something called 0 factorial. Basically, it's 1 over 1, plus there's another 1 over 1 there because that's 1 factorial, and then 1 over 2, and then, boy, it's 1 over 3 factorial, which is 6, and then 1 over 4 factorial, which is 24. And if you just keep doing this forever and ever and ever, it starts to approach that particular value right there. At this level, nobody really cares that much about where it comes from. It's just one of these mythical, magical numbers right here that we're going to have to kind of get familiar with. Now, the good news is, and actually, like pi, you don't really need to know what the decimal value of E is because your calculator has an E button on it, and that's what we're going to use every time that we're doing an E problem. Now, unfortunately here, guys, on my iPad, I can't show you what the TI-84 looks like, but if you look on your graphing calculator right now, please, which I would like you guys to do, if you can find the 4 for me, and then look to the left of that. There's a button to the left of 4 that says LN. That stands for natural log. We're going to learn what that means later on in this chapter. But the second function of that LN button has a little notation on it that looks like this: E to the x power. And again, that's above the natural log button right here, so it's the third button up from the bottom left-hand corner. Okay, so if we wanted to know the value of E, we could go to our calculator. In fact, I'll do this right now. Press second, and then that natural log button, and we get E, and then there's a box over here. And if you wanted to know what it was, just type a 1 in for that power. Any number to the first power is equal to itself. And when we hit enter, we get 2.718281828. There's a lot of 8s in there. I never knew that. And guys, it goes on from there. That's not the end of it, but that's just as much as your calculator will display. So what do we need to know here? E is this crazy irrational number, and it's approximately 2.718. Now, where does it come from? Okay, this is kind of another explanation for it. If you take a look at what's going on right here, guys, this is kind of a variation of that exponential growth model that we talked about back in 7.1. The 1 value out in front was kind of your initial value right here. And then in parentheses, we had 1 plus r divided by n, or x, all to the x power right there. And what happens if we graph that, everybody? That is what's right down here on this graph in blue. So in fact, let me make that blue here so everything matches up. This is the graph then in blue of y equals 1 times 1 plus 1 over x to the x power. And you can see that that is a growth model here, guys, but this function is actually growing, increasing at what we call a decreasing rate. And what I have right above that, if you take a look at the second equation that I've graphed right here, this is just y equals e to the first power, which is approximately 2.718. And what this graph is kind of meant to show you guys here is that as x gets bigger, your exponent gets larger. And that's a good thing. It tends to make your number bigger. But right here, you're adding a 1 over x to the 1 that was already there in the growth factor. But as x gets bigger, that makes the value of this fraction actually smaller. So increasing x kind of has two contradictory effects on the value of your function. It makes the exponent bigger, which helps the function to increase, but it also actually lowers the value of the base of that exponent, which tends to make the function smaller. So we end up with a function in blue that's growing as we head out towards infinity, but it's growing at a decreasing rate. That blue growth function is never going to get higher than this value right here of 2.718. All right, I don't think that really explained to anybody what exactly we just accomplished here or what E really means. So let's take a look at this. I want to revisit a problem that we did in our 7.1 notes a while ago. And in that problem, we said that we were going to deposit $3,500 into an account that was going to earn 4% interest per year. And in that problem, we said that the interest was compounded quarterly. Well, I want to do a little bit of an experiment with this problem right here. And what we're going to do is we're going to change the frequency here of your interest being compounded here. So if we take a look at what's going on right here, I actually want to do this problem 5 different ways, but it should go pretty quickly here, guys. Let's start off with the first one. What happens if your interest is computed yearly? So remember, N, and by the way, I'm sorry, I should reference this formula right over here. We said that we were dealing with a formula in 7.1 of A equals P, which stood for your principal, and then 1 plus, that was an R all over N raised to the NT power. And if we remember here, P stood for principal, R was your interest rate, N was the number of times per year that your interest was computed, and T was the amount of time in years that that amount was going to grow, or that account was going to grow. So if we look at the first thing I want to do here, yearly, we've got to figure out the N value here. Yearly means once per year, so N is equal to 1. So what I'm going to do here to compute this final balance right here, and I'm not going to write this out every time, guys, but here we go. It would be A is equal to P, our principal right here, the amount we deposited to begin with, is $3,500. Then in parentheses, we're going to go 1 plus. R is your interest rate. 4% we said was 0.04. You've always got to divide your percent by 100, divided by N, which in this problem here we said N was going to equal 1. Let's close that parenthesis and we take it to the NT power. N we said was 1, and T, the amount of time in years, was going to be 5 years. So that right there, guys, is what I'm going to type in on the main screen of my calculator, 3,500, and then in parentheses 1 plus 0.04 divided by 1, close the parenthesis, and then take all that to a power of 1 times 5. And if they compute our interest once per year, we end up with a total of, let me get this rounded to the nearest penny, 4258 point. Let's see, I've got 285, so that would be 29 at the end of all that. Although, you know what? For a reason you'll see in a minute, I'm actually going to be more specific. I'm going to write that out. 285,158. We don't usually round money to 6 decimal places, but I might need that to prove my point. All right, let's move on to step 2 here. Now, and this should be an answer we recognize, let's see how this would change if your interest was computed quarterly. Quarterly means 4 times per year. So I'm going to take this one right here and make that a 4 now, and this one right here and make that a 4. So we're really not going to see a very big difference here. In fact, it's almost kind of depressing how little change this makes. But if I change that denominator to a 4 and the one in the exponent to a 4, all right, we made an extra 12 bucks. This one right here came out to be 4,270 point, and I've got 66514 for the cents right there. So yeah, we made $12 more if they compute our interest 4 times a year instead of just 1. Let's do it a third one. Monthly means that this is being computed 12 times per year. And in fact, you guys, this is actually the most common way that interest is computed out there in the real world. They use something called your average daily balance in a month, but then they do almost everything monthly. So what I'm doing now is I'm going back to my calculator and I'm replacing those two 4s that I had there just a second ago with 12s, both on the denominator of the fraction and also up in the exponent now. And here we ended up making, all right, almost $3 extra. Go us. 4,273.488 079. So what I'm hoping you can tell so far is that the more frequently that they compute your interest, the better it is for you in terms of earning money. Of course, that's bad for you if you're borrowing money in terms of a credit card. What if we did it daily? In that case, there's 365 days in a year, so now I'm going to have to type all this in again, but with a 365 there. So 3,500 times 1 plus 0.04 divided by 365. Close the parenthesis and raise to a power that's 365 times 5. And doing that, here we go, $4,274.86289. So we made an extra $1.50 almost if they did it daily. And the last one I wanted to do, knowing how ridiculous this sounds, is what if they computed your interest once per second, which obviously they'd have to have a computer doing and not a person just sitting in the back room at the bank. Now, I already did the math on that to come up with this crazy number right here. The way that I got that, guys, is I thought about it this way. Once per second, there are 60 seconds in a minute. I multiplied that by 60 minutes in an hour times 24 hours in a day times 365 days in a year. So 60 times 60 times 24 times 365, and that's where I got this crazy number of 31,536,000. So now, it sure seems like this is going to make us a ton of money, so let's try it. Back to this equation right over here, but now with that huge number put in the place of the 4s. So 3,500 times 1 plus 0.04 divided by, here we go, 31,536,000. Close your parenthesis and raise it to a power that's n times t, 31,536,000 multiplied by 5 years. And I'm expecting to see a ton more money here. Here's what I got. Not lying to you guys here. Hopefully you're doing this with me. 4,274.915262 cents. So by computing our interest once per second, we made, let's check it out, 5 cents more than if they had done it daily. So this is what I meant when I talked a minute ago, guys, about the idea that increasing n has both a positive and a negative effect on the value of your function here. Increasing it right here makes your exponent bigger, which is good, but then you're actually decreasing the growth factor that you're using. So it doesn't quite have the runaway growth effect that you would really like to see it have. It's kind of a point of diminishing returns at some point. So what are we going to do with this? Well, there's a formula out here, guys, that I need to teach you guys, and this is for something called continuously compounded interest. And what this is, everybody, is a formula that's different from what we did in 7.1, where we were really talking, and in this previous problem too, of what we would call incrementally compounded interest. In this example, some guy in a bank or a computer, more likely somebody who wrote bank software, computes your interest rate every so often, once a year, once a quarter, once a month, once a day, or once per second. But in continuously compounded interest, it is literally happening nonstop. This is actually much more likely to show up in terms of something like the growth of bacteria in a petri dish. Bacteria don't sit there and say, oh, okay, it's the one time per day that we have to reproduce now. They kind of do that nonstop. Well, this is a formula that unfortunately no financial institution I have ever come across in terms of a bank or a stock or a credit card company, nobody ever does. I wish they did, because it's actually much, much simpler than this junk we were doing here just a second ago with this formula. This is the Pert formula. A is equal to P times E to the RT power. And I didn't write everything out because we should already know what everything stands for. Okay, I guess we'll write it out here. A is what we call the final balance at the end of this investment right here. That hasn't changed from before. Capital P still stands for the initial balance, the amount of money that we put into this account. And by the way, it's called P because the word for that is your principal on your particular loan. E doesn't need any explanation, guys. E is E, which is approximately 2.718, but as I said earlier, you don't even need to know that because you have a calculator button to do that for you. And just like before, R is equal to your percentage rate. And by the way, if it ever comes up, that is always your annual percentage rate. And then T is equal to the amount of time in your investment here, but that's got to be measured in years, assuming that this was in fact an annual percentage rate. So A is equal to P times E to the RT power. The Pert formula is much simpler than the incremental formula that we were using before. So I made up one new problem right here, and we'll see where we're at. You're going to invest $10,000, good for you guys, into an account that earns 4.25% interest, and it's compounded continuously. That becomes the most important word in this problem. How much is the account worth after 10 years? Well, as soon as you guys see that your interest is being compounded continuously, we know that we've got to use the Pert formula that we just wrote down. A equals P times E to the RT power. Let's see what we can do with this. A is the final account balance. That's what we're trying to find right here. So we don't know what A is. P is your principal, and that is the $10,000 that you're going to invest at the beginning of this process. This can be a little tricky. Remember, E is not a variable, so the E just stays an E. Your calculator will know what to do with that. But now E gets taken to a power that's R times T. R is your interest rate, 4.25%, but that needs to be expressed as a decimal. Move it 2 to the left, or you could go to your calculator and type in 4.25 divided by 100. That's going to be 0.0425. So all of that is the R value, and then that gets multiplied by T, which is going to be 10 years. That's it, guys. Everything on the right is a constant. The only unknown is on the left, so it's calculator time. And I'm going to go now, and I'm going to type in into my calculator exactly what this right side here looks like. So I'm going to do 10,000. You can hit times here if you want, but you really don't need to. Then I'm going to hit that button I told you guys about before, the E to the X button. I'm going to hit second, and then the natural log button, which is next to the 4 on your calculator. All right, it's the third button up from the bottom left-hand corner. So an E popped up, and then the little box up on the top. So I type in 0.0425 times 10. That's what it looks like. And when we did that, guys, I got a total right here of $15,295, and then I got 0.9042. With most money problems, we just round to the nearest hundredth, so our $10,000 investment here after 10 years is going to be worth, what, about 50% more, a little more than that than it started with, $15,295. To compare that, we probably should do a problem with incremental interest where we would have made a little bit less money on that, but I think we're going to wrap this one up at that point. So part of the end of the homework on 7.2 for you guys is going to be problems like this where they tell you now that you are investing money into an account that's compounding continuously. You're going to use the Pert formula right here in order to answer those questions. All right, guys, that's a wrap on section 7.2, so give that homework a try. Good luck, and let me know when you have questions.